Have you ever wondered how we turn chemicals into essential products like ethyl acetate? Chemical engineering combines science and technology to solve a given problem related to material production and transformation. One key concept in chemical engineering is the application of energy balance and mass balance. Mass is neither created nor destroyed. It only changes form, and by understanding and applying mass balance, we can track how raw materials are converted into products, such as in the production of ethyl acetate. On the other hand, energy balance is about ensuring that energy, in the form of heat and work, is accounted for in the process. When it comes to fluid mechanics, it deals with how liquids and gases move through the system. In the case of ethyl acetate, fluid mechanics helps us design the pipes and manage the flow to keep everything running smoothly, ensuring we get the best results with minimal energy use. As you can see, we have created a specific process flow diagram that maps out each step of the production process using the software called Symmetry. Now, let's walk through the ethyl acetate production process to understand how the reaction works in general. We start with the feedstocks, ethanol and acetic acid, which enter the system as the starting materials. These two chemicals come together in the reactor where they undergo an esterification reaction. And the result of this reaction is ethyl acetate and water. Once the reaction is complete, the mixture moves to the distillation column where we purify the ethyl acetate from the undesired component.
For the non-reactive calculation, we chose distillation column 1 as our unit operations. The feed enters C1 at 70 degrees Celsius and 6.9 atm. The overhead product exits the unit at 90.85 degrees Celsius and 1.9 atm. Meanwhile, the bottom product exits the unit at 196.35 degrees Celsius and 10 atm.
Continuous stirring tank reactor is the reactive unit that we select for this chemical plant. In our calculation, it operates at 343.15 Kelvin and 6.9 atm pressure, which is the suitable condition for the reaction to take place.
Mass balance calculation helps us account for all materials entering, leaving, and reacting in a system, ensuring conservation and process efficiency. There is 4 important things need to be calculated, which is mole flow rate, mole fraction, mass flow rate, and mass fraction. For the mole flow rate, have been given 46.15 kmol per hour. So we need to find the mole fraction. So how to finding mole fraction? We need to divide with the total mole flow rate. So we will get the mole fraction for water. Next, we need to find the mass flow rate. We need to times the mole flow rate with the molecular weight of water. After calculated, we get 831.62 kg per hour. Lastly, we need to find the mass fraction. For the mass fraction, we need to take the mass flow rate divided with total mass flow rate of the top stream. So we will get 0.0809. And repeat the same step for the other component. Voila!
To find out the molar flow rate, we can use equation molar flow rate out equals to molar flow rate in minus stoichiometric times molar flow rate consumed. By referencing the flow rate of ethyl acetate as molar flow rate consumed, we can calculate the flow rate of inlet stream and outlet stream. Next, to determine the mole fraction for both inlet and outlet stream, we use this formula. For mass flow rate, we must multiply mole fraction A with molecular weight of the component. Sum up the mass flow rate for each component to find out the total mass flow rate of a stream. Divide mass flow rate of a component with the total mass flow rate to determine its mass fraction. The total of this mass fraction should be 1.
For the energy balance, we use the equation delta H plus delta EK plus delta EP equals to Q plus W for an open system. By assuming no change in kinetic energy, potential energy, and work done, we can simplify the equation to delta H equals to Q. The reference state for all components is set to liquid at 70 degrees Celsius and 6.98 atm. To calculate specific enthalpy for each component, we integrate the specific heat capacity with respect to temperature. For change in pressure, we use the formula H equals to V delta P. After getting all the specific enthalpies, we can solve for delta H by using the formula delta H equals to summation of flow rate times enthalpy out minus summation of flow rate times enthalpy in.
Now, let me guide you to walk through to the calculation of energy balance on reactive unit. First and foremost, we must set the reference state for each substance, which in this case, I picked the acetic acid. It is in liquid, 25 degrees centigrade and 1 atm. Now, we want to move on to the specific heat enthalpy for acetic acid. First, we must do the hypothetical process path, and it will move from the reference states into the state that we want. And in this case, it will move into liquid, 25 degrees centigrade and 9.86 atm. And then we will get the answers for the first specific heat enthalpy, which is 51.35 kilojoule per mole. Now, we can do the same step for all of the specific heat enthalpy, and we'll get the answers for all the substance. Next, we could move on to the overall equation of the energy balance for the reactive units, which in this case, the rate of enthalpy is equal to the heat of reaction plus the sum of out minus the sum of in. And then I will explain what is the extent of reaction. It is basically, it's equal to the difference of a molar flow rate divided by the stoichiometry of the specific substance that we choose. In our equation, we will get 61.851 kilomole per hour. We'll move on to the calculation and get the answers for this is negative 2.03 kilojoule per mole. And then we could insert all the values for the rate of enthalpy, and we could get this final answer.
First, we have the types of pipes. When selecting the right pipes, material and size are essential. Since we are dealing with chemicals, it is important for us to select the materials that can withstand the production environment as well as compatible with ethyl acetate. For example, we employ carbon steel due to its ability to resist high temperature, corrosion, and super durable according to the Paris Chemical Engineers Handbook. Next, we have the diameter specifications. Diameter of pipe directly impacts the fluid flow. A carefully selected diameter ensures that fluids move efficiently with minimal pressure drop, which is crucial for energy conservation. Finally, we come to the fittings and connections. We employ several valves. Serves to control the flow of materials. First, we've got 90-degree elbow that changes the direction of flow by 90 degrees. Next is gate valves, which is designed to either fully open or fully close the flow of materials in the pipe. Moreover, we've got check valve, which is essential to prevent backflow by only allowing the material to flow in one direction.
Managing pressure drop is essential for system efficiency. Large pressure drop can cause dangerous pressure fluctuations, pipe damage, and other system failures.
Using appropriate equations, we can solve for pressure drops in the pipeline. Now, let's find out how we can get these answers. We multiply the provided molar flow rate with the molecular weight of each component to get the mass flow rate. Next, we divide the mass flow rate with the density to get the volumetric flow rate. For the density of the flow, we use the formula density is equals to total mass over total volume. Lastly, to calculate the absolute viscosity of our mixture is equals to summation of mole fraction of components multiplied by the Lond viscosity of the component.
Hi, my name is Dr. Khairul Daniel. Today I will talk about the impact on transport efficiency and energy requirements. A higher flow rate means more fluid transported in less time, which can improve productivity in industrial process. However, increasing the flow rate also means the fluid may face more resistance due to friction and other factors, which can lead to more energy being required to maintain the speed. The energy needed to move the fluid depends on how fast we want it to flow. A higher flow rate usually requires more energy, especially if the flow is turbulent rather than laminar within the pipeline.
Let's touch on the pump requirements. For this system, the friction factor, determined by the flow conditions and pipe characteristic, affects the power we need. For example, the flow rate of 1 cubic meter per hour, a 10 meter head at a 70% pump efficiency, the required pump power is about 0.035 kilowatts. Now let's talk about the tank sizing, which depends on the production rate, storage time, and the safety buffer. To find the tank's capacity, we multiply the production volumes by the intended storage period and then adds a 10 to 20% buffer. This buffer is crucial. It accounts for any unexpected production surge and prevents overflow, ensuring safe operations.